Hi and welcome back. Today we're going to go over the volume of a sphere and a hemisphere. Should be a pretty short one today. So first, let's remember the surface area formula for a sphere. So remember there was a pretty cool relationship between the sphere and the cylinder that a sphere would fit snugly inside. So when we look at the cylinder here, which has a radius of r, it would have a height of 2r here. So whenever we get over here to the lateral area, the width of the lateral area would be the circumference of the base, which would be 2 pi r, and the height would be the 2r. Well, when we multiply the circumference times the height, the distance between the two bases, that would give us, so 2r times 2 pi r would be 4 pi r squared. And what's interesting about that is that that lateral area, that lateral surface, is exactly the same as the entire surface area of the cylinder that fits in, or the sphere that fits inside, snugly inside that cylinder. So what's really cool is if you can imagine this lateral area that goes around the cylinder is going to be exactly the same area as a sphere. So as this starts to wrap around here, it's actually going to go 60 degrees here. It's 1 radian, right? So we'll go 60 degrees with central angle here, and the part that's left over is going to be from where the parts that are below that overlap. So it actually fits perfectly, which is really, really interesting. So there are a lot of really cool relationships between the surface area of spheres and cylinders, and also we'll see the same thing with volumes of cones, spheres, and hemispheres, of course, and also cylinders working as well. So the first thing we'll look at is this special cone here. So this is a cone with a base, a circle with a radius of r, and the height of the cone is the exact same as the radius. So this is kind of like a unit cone in a sense. So we find the volume of it by using the formula for a pyramid. It's the exact formula for a pyramid and for a cone. So it's going to be 1/3 of the base times the height. Well, the base is going to be pi r squared. So it's the formula for the cone would be 1/3 of pi r squared times the height, which in this case we set that to be equal to r. Well, we can combine these r squared times r. That's really r times r times r, which would be r cubed. So that's going to leave us with 1/3 pi r cubed. So that's going to be the volume of this special cone over here. Now, if we look at a hemisphere, so the hemisphere is just going to be, we're going to set it so that it has the exact same radius of r and the exact same height of r as well. So if you think about it, the hemisphere obviously is going to have a larger volume than the cone, given the same dimensions that we see here. But what do you think the relationship between those are? What do you think that ratio or that scale factor between those two might be? So what's interesting is it's actually exactly half. So the hemisphere is going to be twice as big as the volume of the cone, which is pretty interesting. So the formula for the hemisphere, volume of hemisphere, is going to be 2/3 pi r cubed. So 2/3 pi r cubed, which is twice as much as the cone with the same basic dimensions, which would be 1/3 pi r cubed, which came from our formula from the pyramid. So then if the hemisphere is 2/3 pi r cubed, then the volume of the sphere is just going to be twice that amount, which would be 4/3 pi r cubed. So 4/3 pi r cubed. So our cone, which is the red shape here, right? The red figure is going to be 1/3 pi r cubed. The hemisphere is 2/3 pi r cubed, which is twice as much. And then the sphere is twice as much as the hemisphere, which is 4/3 pi r cubed. So those are our formulas, pretty simple to work with. Let me show you how to put them in the calculator if you're using a TI-30 XS Multiview. So on this one here, we have a sphere, so we want to use the 4/3 pi r cubed, not the 2/3, because it's the whole thing, not the half. So first thing we might put it in the calculator is using the n over d button. So I'm going to do 4 numerator over denominator thirds, and if you can use that button on the calculator, it'll make sure that you put it in right and that you get the right answer. So we're going to do 4/3 and then pi times the radius cubed. Now I want to leave my answer in terms of pi, so I'm not going to put the pi in the calculator. I'm just going to leave it in my answer at the very end. So I need to do the radius squared, which in this case our radius is 3. So what I'm showing here are the keystrokes. So important thing to do, so we put in the 3, then we need to arrow over to the right to leave the fraction. So then we're going to do 3 caret, which is our caret button here, which means to the power of 3, and that's going to give us a total answer of 36. So 3 squared, or 3 cubed, is going to be 27. 4/3 of 3 cubed is going to be 36. So our volume is going to be 36 pi cubic centimeters. So there would be 36 times pi, which if we wanted to know exactly what that value would be, like approximation, we just multiply it by pi. Of course, I have to convert it to a decimal, which is going to be 113 approximately of these centimeters cubed, cubic centimeters. All right, so that was it. Just 6 minutes for the kind of introduction here, just really showing you the formulas, and we'll look at the last problem as well and kind of investigate some more of that stuff together anyway. So on number 1, we just want to use the formula, so we want to find the volume. This is a sphere, so we're going to do 4/3 pi r cubed. So the first thing we might want to do is take the radius, which they give us 8, and then take it to the 3rd power. So we can do that first. So 8 caret 3. And then all we have to do after that is multiply it by 4/3. So we can do that by multiplying by 4 and then dividing by 3. That's probably the easiest way to do it if you don't have one of these calculators. So that's going to give us 682.6 repeating. And it's also still in terms of pi in this case. So number 4, on this one we have to be a little careful because we're dealing with a hemisphere. So it's going to be, our formula is 2/3 pi r cubed, and also they give us the diameter. So we want to take half that, which would be 21 to the 3rd power. So I'm going to do 21 caret 3, and then I'm going to arrow over or multiply it by 2/3 this time. So times 2 and then divide by 3. It'll be reducing, which is 6,174 pi millimeters cubed in this case. All right, number 10. So you've seen problems like this when we did surface area, so we do still need to know how to work backwards, and you saw some of those on the test as well. I will put out the video for the practice test probably on Saturday. I'm just waiting for more people to take it, more people to take the practice test. So I'll put that out this weekend definitely, so you guys can see what you did wrong on the last test. All right, so an asteroid with a circumference of 83.92 meters. We want to first solve for the radius and then find the volume. So the first thing I'm going to do is I'm going to plug in the formula. The circumference that they gave us is equal to 2 times pi times the radius. Well, if I want to solve for the radius, the first thing I have to do is divide both sides by 2 pi. So that's what I'm going to put in the calculator. I can do the N over D button if I like. That'd be kind of nice. So 83.92, and then I'm going to divide that by 2 pi. Now, if you're doing this without the N over D button, you have to divide it by 2 and then divide it by pi. If you divide by 2 pi, it'll divide the 2, but then multiply the pi, so you would get a different answer than what I got. All right, so that's what I'm getting, and that's going to be the value for the approximation for the radius, so 13.36, and that would be meters. Then to find the volume, once I have the radius, this is an asteroid, so we're talking about a sphere, the whole 4/3, right? Not just 2/3, not half. So I want to multiply that, or take the radius and cube it first, so caret to the 3rd power. And notice the previous answer, I'm not just using the 13.36, I'm using the entire previous answer, which is really this value here. So all the precision in the calculator. If you're getting slightly different decimals, it's probably because you're rounding and you're getting rounding error. So to avoid that, just keep using the previous answer. So we're going to take that to the 3rd power, and then I guess I'll go ahead and do that. And then I need to multiply it by 4/3. So times 4, and then divided by 3. You can do that as well. Okay. And so our volume, and that's going to be in terms of pi still, is going to be 3,176.84 pi millimeters, or it should just be meters. So meters cubed. Okay. So simple process, just divide by 2 pi first to get the radius from the circumference, cube it, then multiply it by 4/3, and add the pi to your answer when you're done. All right, number 17 is a pretty cool problem. So we have a globe that is packaged and shipped in a cube box. It's the dimensions are 18. Let me pull up the assignment over here so I can see read along, see what's going on. Okay, so you buy a cool globe with a diameter of 18 centimeters. By the way, the world is round. Yes. Never goes away. You buy it online, they ship it to you in a box that's in the shape of a cube. The globe fits snugly in the box and touches all 6 sides of the box at one point. All right, so all 6 faces at one point. It's tangent to it, in other words. So what is the volume of the box? Well, if we have a diameter of 18 centimeters, then that means that the dimensions are 18 by 18 by 18. So to find the volume of the box, the base would be the square on the bottom would be 18 squared. So 18 squared, it's going to be a rather large number. And then we're going to have to multiply that by the number of layers, which would be 18. I know you can just do 18 cubed. It's the same idea, which is 5,832. That would be in centimeters cubed. Next thing we want to do is find the volume of the sphere, the globe. So that's going to be using a different formula. So now we're using the radius instead of diameter. So we have to cut that in half, which would be 9, right? So 9 cubed, and then multiply it by 4/3 pi. And you can look on the answer bank and see if your answer is left in terms of pi. If you don't see the answer, go ahead and multiply it by pi in your calculator until you get something that matches the answer bank. All right, so on this one, we're going to do 9 cubed, so 9 to the 3rd power. Then we're going to multiply that by, so times 4 divided by 3. We can also use the fraction button if we want. Okay, and remember this is left in terms of pi. I guess I can, if you have a pi button, you can go ahead and multiply it, and the calculator should leave it in terms of pi. So that's going to be 972 pi, which I believe is your answer. Yeah, so we didn't actually have to multiply the pi and give a decimal approximation. We could keep the precision. I like that because there's no decimals involved here too. All right, so what's the difference? What's the difference between the box and the sphere, the globe, right? The wasted space. So all we have to do is subtract these two values. So I'm going to start out with my 5,832. And then from that, I'm going to subtract. Now, if you have a calculator, you can actually just arrow up and kind of copy and paste it in that way, which is really nice, which will give us a difference of 2,778 centimeters cubed. And then we have our decimals, we round to the hundredths place. And then the next question, they tell us that if each packing peanut takes up an average volume of 16 cubic centimeters, then how many packing peanuts would we expect to be shipped with our globe? So if each one takes up 16 cubic centimeters, all we have to do is take this volume that has to be filled with packing peanuts and divide it by the average volume that is filled up by each individual packing peanut. So I'm going to take this value with all of its precision and simply divide it by 16, which should give me the number of packing peanuts on average that we would expect, right? So 173.6. Well, we want to go ahead and round because we're not going to deal with a fraction of a packing peanut. So we're going to go round it up to the nearest whole, the whole peanut, which would be 146, which is approximately 174. All right, 18. So on this one, we want to compare this kind of unit cone with the radius and the height being congruent to the hemisphere, to a cylinder that has the same height as the radius, and then to finally the sphere. So we know the formula for the hemisphere and sphere is 2/3 pi r cubed and 4/3 pi r cubed. We want to write these equations in terms of r and pi as well. So we can compare it with the pi r cubed to the 2/3 and the 4/3 pi r cubed. We obviously already know that the hemisphere is going to be half the volume of the sphere. So for this one, to find the volume, first we find the area of the base, which would be pi r squared, because we're dealing with a circle, and then we multiply that by its height divided by 3. So that's going to be 1/3 pi r cubed. So we have pi r squared for the base times the height, which is r divided by 3. Well, we can go ahead and combine r squared and r, because r squared is r times a third r, which we can use our exponents to combine to give us r cubed. So this is going to be 1/3 pi r cubed. So then notice the 1/3 pi r cubed is exactly half of the volume of the hemisphere, which is quite interesting. And then next one that we have to look at is our cylinder here. Well, very similar process to the cone, except now we're no longer dividing it by 1/3. So it's going to have a base of pi r squared times a height of r, because there's r layers to that. And then we don't have to divide it by 3 because it's not a cone or a pyramid. So it's just simply going to be pi r squared times r, which is pi r cubed. And pi r cubed, if we notice here, is going to be the difference between these two, right? So if I added the volume of the cone plus the hemisphere together, 1/3 plus 2/3 would give us the full, well, 3/3 if you want to think of it that way, but the full pi r cubed. And then if we add an additional cone on top of that, that would give us the volume of the sphere. So kind of you have 1/3, 2/3, 3/3, and 4/3, which is actually really cool. How all that works. Now, those formulas are derived using calculus properties that I can't necessarily explain to you, but I can show you and kind of lay this out. And they're all their formulas are written in terms of R. So these kind of unit cones and hemispheres and cylinders and spheres, I think are still kind of useful to kind of piece that stuff together and see how it works. So I believe that's the last one. Yeah, that's the last one that I'm going to do. And that actually wasn't number 18. I apologize, that was number 19. So you'll need to do 18 on your own. So we only have one more lesson after this, which is kind of a unit analysis between looking at the similar three-dimensional figures and their scale factors in one-dimensional units, two-dimensional areas like surface area, lateral area, and then their volume or density as well, which is going to be three-dimensional. So I think you're going to enjoy tomorrow's lesson. It's pretty advanced. I think you're going to like it. I got some pretty fun discussions that I get into there. So it'll actually be the last lesson that we have for the tested material over geometry. Then we'll take the practice test on Tuesday. And then Wednesday, Thursday, and Friday, I'm going to show you guys my three favorite extension activities that we would have done at the end of the year. So I think you're going to enjoy those as well. So we are almost done. We only you made it to the end of the week, so we only have one more week left, and then summertime. So I will see you guys later.